I am repeating again. Hi everyone. In the last lecture, we have described the spectral theorem for self-adjoint operators. So we have shown that if T is a self-adjoint bounded operator defined on Hilbert space H, then there exists a unique spectral family E lambda of T such that T can be written as integral A to B lambda dE lambda, where A is less than the lower numerical bound of T and B is bigger than or equal to upper numerical bound of T. Now today we are going to discuss about one more version of the spectral theorem, namely the multiplication form of the spectral theorem. So this version of the theorem we have already seen for compact operators. If T is self-adjoint and compact, in fact we have shown it for normal operators also. If T is compact normal, then there exists a unitary operator U such that T equal to U m phi U, U star m phi U, where U is a map from small l to n into l to n. This is unitary. This is unitary, and phi of T is the function which is identity defined on the spectrum of T, and m phi is the multiplication operator induced by phi. So we were able to show that T is unitary equivalent to a multiplication operator, and we know that the multiplication operator is normal always, and we know that also the unitary equivalence preserves the spectrum and many more properties of the operator T. So in this way it is easy to look at the compact normal operator, which is unitary equivalent to multiplication operator, and studying the multiplication operator properties, we can actually get the properties of T. Now we can ask the question, can we drop the condition that T is compact? In fact we can do this. Today we are going to prove this result for self-adjoint operators. So let us quickly state the theorem. Let T be a self-adjoint operator which is bounded, then there exists a finite measure mu on the Borel subsets of spectrum of T, and a phi from L infinity of mu, which is real valued, and a unitary map L2 of mu into H such that U star Tu equal to m phi, where m phi is a multiplication operator induced by phi. Okay, that means given any self-adjoint operator, we are going to show the existence of three things. One is the finite measure mu on the Borel subsets of spectrum of T, and phi is in L infinity of mu, and a unitary map U such that U star T U equal to M phi. Okay. So let us quickly recall the proof of the compact normal case. So we were able to show that since T is compact normal, then it has an orthonormal set of eigenvectors. Now using those eigenvectors, we were able to define unitary map. But in the case of self-adjoint operators, we know that there exist self-adjoint operators which does not have eigenvalue at all. So in this case, we cannot actually follow the earlier proof that we followed for compact normal operators. So for that reason, we are going to introduce a new concept called cyclic vector. So let us take a bounded operator a vector xi which is non-zero is called a cyclic vector for T if you look at the span closure of xi, T xi, T square xi, so on, this span closure of this xi T xi T square xi should be equal to H. Or we can actually express this in a different way. Look at all the polynomials of T and evaluate at xi where P is a polynomial. Of course, polynomials are defined on the spectrum of T. So this should be dense in H. These two are equivalent. Okay. So instead of eigenvectors or orthonormal basis, we are going to use this concept in the case of self-adjoint operators. Let us look at a few examples. Let us take let R be the right shift operator. R of x1, x2, x3, so on is 0, x1, x2, x3, so on for every xn in L2. Okay. Now if you look at the vector, let us take xi to be 1 0 0 0, so that is the vector E1. Then we can look at span closure of xi, r square xi, so on. This is nothing but span closure of xi is E1, then rxi is E2, then E3, so on. We know that this is an orthonormal basis for L2, so hence it is dense. So the conclusion is that xi is a cyclic vector for R. Okay, so let us look at the left shift operator, which is R star. Let us look at R star of xi. So let us look at span closure of xi, R star xi, R star square xi, so on. This is nothing but span closure of, so this is E1, R star xi, that is left shift operator, acting on E1, so that is 0, so remaining all vectors must be 0. So this is nothing but you will get span of E1. This is a one dimensional space, so cannot be equal to okay. That means xi is not a cyclic vector for R star. So in this case what we do is we can define something called a cyclic subspace. Let us define a subspace M of H is called a cyclic subspace for T if there exists a vector xi which is non-zero, such that if you look at the span closure of xi, T xi, T square xi, so on, this is equal to M. So if M is a cyclic subspace and if it is dense in H, then xi is a cyclic vector for T. Okay. So example, span E1 is a cyclic subspace for E1 itself. Sorry, it's a cyclic subspace for R star. Okay, let us look at one more example of cyclic vector. Let us take a map T from C3 into C3 by T of x, y, z is given by x, y, 2z for every x, y, z in C3. So the matrix of T with respect to the standard orthogonal basis is, this is 1 0 0 0 1 0 0 0 0 2. Okay. Now let us look at whether this operator is cyclic vector or not. So we claim that T has no cyclic vector. Okay. So let us see. Suppose xi is a cyclic vector. Let xi equal to xi1, xi2 be a cyclic vector for T. Then if you look at P of T, let P be any polynomial. Then P of T at xi we will get P of 1 0 0 0, P of 1 0 0 0, P of 2 xi1, xi2, xi3. So this is nothing but P1 xi, xi1, P of 1 z2, P of 2 z3. So if P of 1 is P is a general polynomial. So if P of 1 is non-zero, we can take P of 1 to outside. This is z1, z2, P of 2 by P of 1, z3. Okay. Now in that case, if you look at, let us take eta to be minus z2 bar, z1 bar 0, this is in C3, and if you look at P of t xi inner product with eta, this is P of 1 will come out. So this will be minus j1 j2 minus j1 j2 plus j1 j2, that is 0. So you will get minus j2 j1, this is 0. That means this eta is orthogonal to P of t xi. So from this we can conclude that T has no cyclic vector, therefore T cannot have a cyclic vector. Okay, so in this case we already mentioned that we can look at the cyclic subspace and work with the cyclic subspace. Okay, now suppose T doesn't have a cyclic vector. In that case, so let us take T to be self-adjoint and xi to be non-zero. Then let us look at, so let us start with xi1. Okay, so in that case let us define h1 as span closure of xi1, t xi1, t square xi1, so on. Okay, so if h1 equal to h, then we can conclude that xi is cyclic for t. Now if h1 is not equal to h2, that means if h1 is strictly contained in h, and we can easily show that h1 is a invariant subspace for t. So let me write as a remark. H1 is an invariant subspace so in fact it is reducing because T is self-adjoint. This we know already. We know that if a subspace is reducing invariant subspace for the operator, then its orthogonal complement is invariant for the adjoint of the operator. Since h1 t equal to t star, we can say that every invariant subspace is reducing. So in this case h1 is an invariant subspace and in fact reducing subspace. If h1 is properly contained in H, then we can say that h1 plus h2, h1 plus h1 perp and h1 perp is non-zero. Now h1 perp is also Hilbert space, and we can pick up a vector named xi2 and look at the span closure of xi2, t xi2, so on. And in fact here let us say T1 is T restricted to H1. It's a map from H1 into H2, H1 into H1. Okay, so let us pick up xi2 from H1 per, which is a non-zero vector. So define H2 as span closure of xi2, T xi2, T square xi2, so on. Now we can easily say that clearly H2 is orthogonal to H1 the way we have chosen H1 and H2. Now we can continue this procedure, and using the Jones lemma we can actually write down H as direct sum of cyclic subspaces. So in proving all our theorems, we are going to assume that H to be separable, because when H is separable we get the cyclic subspace to be countable, otherwise we will get uncountable, and dealing with countable cyclic subspace is easier than dealing with uncountable subspaces. So for that we assume that H is separable all the time, and for the non-separable case also the proof follows in the similar lines, but there are more complications. You see, H is separable. Okay, so now what we can do is continuing this procedure and using Jones lemma. So we get that H is orthogonal direct sum of Hn, n equal to 1 to infinity, and T anyway we can write as direct sum of T restricted to Hn, and so let us say this equal to Tn, where Tn is nothing but T restricted to Hn. Now we can say that each Tn has a cyclic vector, because each Hn is cyclic subspace for T. Okay, so this is the way when there is no cyclic vector we can actually reduce the case to cyclic vector and argue using the cyclic vector case. Okay, this we are going to use in our proof. Now let us try to prove the spectral theorem. Let us look at the proof of the theorem. So we are given a bounded self-adjoint operator from H to H. This is T, and we want to find a finite measure mu and a function phi. So using this function we can look at the multiplication operator induced by phi, and we want to find a unitary map from L to mu into H. In this case this will be U star, such that this diagram commutes. That means we want to prove that U star Tu is M phi. So first we have to find a finite measure mu. Okay, let us look at the ideas of the proof before going into the details of the proof. Okay, the first one is, if A is a self-adjoint bounded operator, then the spectral radius of A and norm of A are the same. The second is the Weierstrass approximation theorem. Which says that if you have a continuous function defined on a closed and bounded interval AB and taking values in R, there exists a sequence of real polynomials Pn such that Pn converges to F uniformly. The third one is the Riesz-Markov theorem. Which can be stated as follows. Let us take K to be compact Hausdorff space and lambda is a map from C of K, that is set of all continuous functions from K into C, and this is a map from C of K into C. This is linear bounded and it is also positive. That means it maps positive elements of C of K into positive elements of C, that means positive real numbers. F is in C of K, F is positive, this should implies lambda of F should be bigger than or equal to 0. Then there exists a finite measure on the Borel subsets of K such that lambda F can be represented as integral over K F d mu for all F in C of K. Okay, so let us call this equation as star. With the help of these three results, we are going to prove our theorem. So let us look at the proof. So first we want to find a finite measure. For that we have to apply Riesz-Markov theorem. To do that we have to define a functional lambda from C of K into C. So in our case K is nothing but spectrum of T. To prove the result, we consider two cases. The first one is T as a cyclic vector. Case 1. T has a cyclic vector. So let xi be a non-zero cyclic vector. Now define L from PR of spectrum of T into R. Sorry, this is H by this PR of spectrum of T is nothing but the space of all real polynomials defined on spectrum of T. We know that spectrum of T is compact. So if you take any polynomial, define this as inner product P of T xi with xi. So here P goes to, in fact we get this is C R, because P of T is self-adjoint and inner product P of T xi with xi is real number. This is for every P in PR of spectrum of T. Now we can easily check that this is a linear. L is linear. We want to check that this is also bounded. So next consider norm L of P. This is modulus L of P is inner product modulus P of T xi with xi. So by the Cauchy square inequality, this is less than or equal to norm of P of T xi into norm of xi. So this is less than or equal to norm of P of T norm xi square, and we know that P of T is self-adjoint, and norm of the self-adjoint operator is exactly the spectral radius of P of T into norm xi square. This is supremum of P of lambda mod P of lambda, where lambda is coming from spectrum of T. This is nothing but sup norm of P into norm xi square. So we can conclude that therefore L is bounded and norm of L less than or equal to. So we have bounded linear operator from PR of spectrum of T into R, and we know that a set of all polynomials dense in C of spectrum of T by the Weierstrass approximation theorem. So we can extend this L to the closure of this space, that is C of spectrum of T. So let us call this extension by L tilde. Let L tilde is a unique extension of L. So L tilde be the unique continuous extension of L. So next claim is that, so again we use the Weierstrass theorem here. First we show that L tilde is positive on the polynomials. So let us take P to be a polynomial. This is positive. Then we can have P can be written as Q square for some Q in this space PR of spectrum of T. So then we can write L tilde of P is nothing but L of P. Now that is nothing but L of Q square. If you look at the definition of L of Q square, that is Q square of T in xi inner product with xi. So this is now this can be written as Qt of xi into Qt of xi. So this is now Q is self-adjoint. Q is real valued, so Q of T is self-adjoint. So this is nothing but norm of Qt xi square, which is always positive. So on the polynomial space, L tilde is positive. Now we want to show that L tilde is positive on C of spectrum of T. So let us take F to be positive in the C of spectrum of T. Then we can approximate square root of F by sequence of polynomials Pn. Let Pn be a sequence of polynomials such that Pn approximate square root of F in the subnorm of C of spectrum of T. Then we can say that Pn square converges to F in the subnorm of spectrum of T. Hence we can say that L tilde of F is limit of L tilde of Pn square but on polynomials L tilde and L are same. So this is limit n tends to infinity L of Pn square. But we know that this is positive because Pn square is positive. L of Pn square is always positive. So this is positive. So hence we can say that L tilde is bounded, linear, and it's also positive. We can apply the Riesz-Markov theorem. So by the Riesz there exists a finite measure mu on the Borel subsets of spectrum of T such that L tilde of F is nothing but integration over spectrum of T F d mu. So let us say this is equation double star. Okay, so we got a measure mu. Next we want to define phi and multiplication operator induced by phi and a unitary operator. Okay, so define phi of lambda equal to lambda for every lambda in the spectrum of T. Okay, since spectrum of T is compact, we can say that this is continuous. In fact, it is bounded. Okay, now we want to define a unitary map U such that U star Tu is M phi. So define U naught from PC of spectrum of T into H by U naught of P is P of T xi. This is for every P in PC of spectrum of T. Now here PC of spectrum of T is the space of all complex polynomials defined on spectrum of T. Okay. Now our claim is that this U naught is an isometry. U naught is linear isometry. Okay, so let us take norm U naught P square. So let us take P from the polynomial space. Consider. So here once we show that U naught is an isometry, we can extend it to the closure of PC of spectrum of T with respect to L2 norm, so which is nothing but L2 of mu. So here look at norm U naught of P square. So by definition this is norm of Pt xi square. This can be written as inner product of Pt xi with Pt xi. Now this is nothing but Pt star Pt xi inner product with xi. Now here P is a complex polynomial. Now when P is complex polynomial, Pt star is nothing but P bar of T, P of T xi xi. So this is nothing but mod P square of T xi inner product with xi. So let us look at by star. If you look at So this is nothing but L of mod p square. If you look at this one, this is nothing but L of mod p square and by definition this is integration over spectrum of t mod p square d mu, that is nothing but L2 norm of p square. So this, from this we can say that norm u naught of p equal to L2 norm of p. That means u naught is in isometry on PC of spectrum of t. Here it is with respect to the L2 norm. Now this space is dense in L2 of mu, hence we can extend this isometry to the bigger space L2 mu. So let U be an isometric extension of. So here this isometric extension is unique. To L2 of mu. So that means we can say that U is a map from L2 of mu into H such that U naught restricted to PC of spectrum of t is nothing but U naught. Okay. Now we have range of U equal to range of U closure, and range of U contains range of U naught, but range of U naught is nothing but U naught is also isometry, so range is closed. So this is nothing but span of, so U naught is map from PC of spectrum of t into H. So this is span of PT of xi, where p is a polynomial. But we know that this is dense in H. So that means U is onto. Okay. So that means U is isometry plus onto, hence it must be unitary. So our next claim is that U star Tu is M phi. Okay. So we have, so let us take, so again here we want to show that these two operators are same on the dense subspace, namely polynomials. So let us take Q be a polynomial, and let us write Q tilde of lambda is lambda Q lambda. So then we have U star of Tu acting on Q. This is U star of T. This is U naught Q because U and U naught coincide on polynomials. This is U star T. U naught Q by definition. So U naught of any polynomial is nothing but polynomial of T into acting on xi. So this is Q of T xi. Now U star is inverse of U, so we can write this as U inverse of. We can say that this is by functional calculus for self-adjoint operators. So this is Q tilde of T xi, because Q tilde is nothing but lambda times Q. Now by the definition of U inverse, this is exactly U inverse of Q tilde T xi is nothing but Q tilde, but this is nothing but lambda times q, but phi of lambda equal to lambda, so we can write this is now phi into q. This is phi q, or we can say this is exactly m phi acting on q. So u star tu and m phi coincide on the space of polynomials. Since the polynomials are dense with respect to L2 norm, we can say that we can conclude that u star tu is nothing but m phi. So this completes the proof. In the case when T has a cyclic vector, namely xi. So we assume that xi is a cyclic vector for T. Okay. Okay, next we can look at the second case. T has no cyclic vector. So in that case we can write write H as direct sum of Hn, where each Hn is a cyclic subspace and Hn reduces T. So this we have seen earlier. So let us write Tn as T restricted to Hn. This is a map from Hn into Hn for all n in n. Then we can write T as direct sum of all these Tn's, n equal to 1 to infinity. Okay. Now we know that each Tn has a cyclic vector because Hn is cyclic subspace for T. Each Tn has a cyclic vector and each Tn is self-adjoint for every n. So by case 1 we can actually write down each Tn as a map which is unitarily equivalent to a multiplication operator. So by case 1 there exists mu n, phi n and un, where mu n is a finite measure on the Borel subsets of spectrum of Tn, and phi n t equal to T for all T in spectrum of Tn, and the third one is this un is a map from Hn into Hn unitary such that un star Tn un is multiplication induced by phi n for every n in n. This is by case 1. Now we can write since T equal to direct sum of Tn's, we can say that this is unitary equivalent to direct sum of m phi n on the space direct sum of L2 of mu n. And here in fact we can say that this is L2 of spectrum of Tn mu n. Now we want to regard this multiplication operator as a multiplication operator on some L2 space, and this direct sum of L2 spaces we want to regard as L2 of mu for some finite measure mu, and this direct sum of m phi n is a multiplication operator and is by some phi coming from L infinity of mu. So that's what we want to show. So so for that let us write xn is spectrum of Tn for every n in n. So divide with appropriate number such that mu of xn is less than or equal to 1 by 2n for every n in n. This we can do. Okay. Now we can actually relabel xn's in such a way that they become disjoint and their union is x. So relabel, in fact rearrange elements of the sets xn such that xn intersection xm is empty for every n not equal to m, and this x is nothing but spectrum of T. So let us write x equal to spectrum of T. We can write this union of xn. Okay. Now we want to define a measure on x. So let E be a subset of x. So we say that define E to be measurable if and only if E can be written as union En, countable union of measurable sets, where each En is coming from xn. En is measurable. Okay, so if you collect all those sets, we can show that this gives a sigma algebra on X. Now, so let us take S to be union Sn, n equal to 1 to infinity, where Sn is contained in Xn for every n in n. This is measurable. That means we are taking a measurable subset of X. Define, we want to define a measure mu of S to be summation n equal to 1 to infinity mu n of Sn. We know that mu n of xn is less than or equal to 1 by n. So because of that, this series is convergent and this measure is finite. So clearly mu is finite. So that means, so we can say that x mu is a finite measure space. Okay, so we got mu. So from that we can construct L2 mu. Now define phi of t to be phi n of t for every n in n, and we know that phi n of t equal to t for every t in xn. Okay, so we know that t is unitary equivalent to multiplication operator, direct sum of multiplication operators induced by phi n's, and we want to show that direct sum of m phi n is unitarily equivalent to m phi, where phi is given in this way. So clearly we can conclude that this phi is in L infinity of mu. Okay, so we can check that m phi is unitary equivalent to direct sum of m phi n on L2, direct sum of L2 spaces. Okay, here we can actually give a unitary equivalent between the spaces direct sum of L2 xn mu n into L2 of x mu. So using that we can actually show that m phi is unitary equivalent to direct sum of these multiplication operators, and we know that t is unitary equivalent to direct sum of m phi n. So as t is unitary equivalent to on L2 xn mu n, so we can conclude that t is unitary equivalent to m phi on L2 x mu. Okay, so we have shown that t is unitary equivalent to m phi, where phi is nothing but phi and t. So phi and t is nothing but t for every t in xn. That means we are decomposing x as disjoint union of xn's, and on each xn phi of t is an identity map. Phi of t goes to t. Okay, in other words, phi of t is nothing but phi 1 of t, phi 2 of t, phi 2 of t, comma phi 3 of t, so on. It is identity map on each component. Okay. So the difference between the earlier spectral theorem and the current spectral theorem is that we were able to represent t as integral of lambda d lambda, where e lambda is the spectral family generated by t, and we know that that is a unique spectral family. Here the measure that we are getting need not be unique, and when you are representing t as unitary equivalent to a multiplication operator, so that representation need not be unique. So we can actually find simple examples when I is the identity operator on some L2 space. We can actually show that you can get different representation as a multiplication operator. This completes the proof of the theorem in the second case. So let me quickly recall what we have done in this case. So we are applying the case 1 for t equal to direct sum of Tn, where Tn is a map from Hn to Hn, and each and Hn is cyclic subspace, and we can from the case 1 we can show that we can conclude that each Tn has a cyclic vector. So from that we can actually get a triple mu n phi n u n, where mu n is a finite measure on the Borel subsets of spectrum of Tn, and we are defining phi n of t equal to t, and un equal to un is a map from Hn to Hn, which is unitary. So actually we are adjusting the direct sum of multiplication operators defined on direct sum of L2 of spectrum of Tn mu n with, we are writing that as m phi on some L2 space by identifying direct sum of L2 of spectrum of Tn mu n with some L2 of x mu n, where x is spectrum of t. So L2 of x mu, where x is spectrum of t, and mu is measure which is depending on mu n's. Okay, so that is a whole idea, and the difference between this spectral theorem, that multiplication form, and the earlier spectral theorem that we have proved, the integral form, there is a difference that the integral form is a canonical form, in the sense that there exists a unique spectral family generated by T, such that T can be represented as an integral, while the unitary equivalence to multiplication operator is not canonical. So let us see one example. So let us take let H be a separable Hilbert space. And I from H to H is the identity operator. Now we can write I as unitary equivalent to some multiplication operator. So define U from L2 of 0 1 with Lebesgue measure into itself, so be a unitary. Then the multiplication operator m1 induced by the constant function 1, so we can actually look at u star m1u is nothing but the identity operator on H. So here m1 is a map from L2 0 1 with Lebesgue measure into itself. So sorry, here it is H. M1 at phi of t is 1 into f of t, that is f of t. So another way of representing is that we can define some w. So let us look at L2 of natural number with counting measure. So this is counting measure, and take w to be, so let us take w to be a unitary map. So then again we can say that double star m1w is nothing but identity, where m1 is the multiplication operator on L2 n mu into L2 n mu, such that it sends f of t into itself. So w is here again H. Okay, so that means the spectral theorem multiplication, which is a multiplication form, is not canonical, while the spectral family version is, the integral version is canonical one. So this is the difference between these two spectral theorems. I'll stop here. Thank you very much.